Hello, Analysis 1A. Here we are in week 3, learning about limits, and there was some homework from recent weeks which we're going to hand in today. The homework load for this unit is quite light, I think, because a lot of the problems aren't too time-consuming, and we're going kind of a lot slower than the book does because we're looking at things a little bit more theoretically. Well, there was a homework assignment from last week that was due on the middle of last week, or I guess it's the end of last week, I don't know, due on 210, from page 74. This was section 2.2, which just introduced the definition of a limit using epsilon delta proofs, and then there was some homework due today. Today's Wednesday, the 17th, so it was due Tuesday and yesterday and today from section 3.3. Also from the textbook. I think in a normal year I kind of barely go over these problems because a lot of them are like really, really easy, simple, little, quick, just kind of do it problems. Okay, that's great. Well, hopefully then these two assignments took you, very little time. Let's go over there. One or two interesting things that are going on. I circled the problems that I intend to go over because I thought these were the only ones that deserved discussion. The rest of them were sort of very easy. Hopefully you can check your answers in the back of the book. And all right, let's go then. Page 74. So I'm going to go over these now. Post this today, and then we'll hand in this homework. So this is from page 74, but actually by the time we get to number 25, we are actually on page 76. So number 25 on page 76. What is it? Well, it gives you a piecewise function. This is barely a calculus problem. This is really a pre-calculus problem. It gives you a piecewise function defined as follows. Follow the x squared rule for x less than or equal to 2. Follow the rule 8 minus 2x for x between 2 and 4. And follow the rule 4 for x greater than or equal to 4. Okay, so this is a piecewise function. You learned how to do this in pre-calc. Maybe I'll just erase these commas because it's kind of distracting. Yeah, let's go. Let's make a picture and then just kind of look at it. So what does the picture look like here? Well, first of all, 1, 2, 3, 4. 1, 2, 3, 4 might be a good idea. Let's see. So I follow for any number greater than 4. I just follow the rule 4. So it's a constant function. Between 2 and 4, what do? Well, when x is 2, well, maybe I'll just fill it in, kind of one piece at a time. For x less than 2, I should follow the rule x squared. So when x is 2, in fact, the output is 4. So that's 4. And now I'm just following the rule y equals x squared for all of those. So we got something that looks like this. And in between 2 and 4, I'm supposed to follow the rule 8 minus 2x. All right. Well, when x is 2, where am I? Answer 4. Oh. And it's a line with slope negative 2. By the time I get to 4, where am I? Answer 0. And so, filling in the kind of last little piece of this, I have now done all of my pre-calculus correctly. And I have a picture of a function, which is a parabola, then a line with negative slope, then a constant function. Now, finally, we have some calculus, which is also barely calculus. It asks you a question. Identify the values of c for which the limit exists. And the answer is that the limit as x approaches 4 of this function does not exist because the limit from the left is 0 and the limit from the right is 4. But any other x value, the limit does exist. So the answer is C, the set of values for which the limit exists is, well, I guess it's just everything except 4. That's pretty much how I would write my answer. Okay, good. One down, a couple to go. 27 says to graph a certain function. Maybe I'll just do it here. 27 says graph a certain function. Here is what you have to do. F of 0 is undefined. Okay, check. The limit as x approaches 0 of the function should be 4. So local behavior should be 4, even though it's undefined at 0. F of 2 should be 6, but the limit as x approaches 2 of the function should be 3. Okay, I don't think this is that hard to do. Let's go. Near 0, the function should be basically 4. So I'll go up here to 4, and I'll put a sort of open circle there, all right? Because in fact, f of 0 should be undefined. What else do I know? That f of 2 should be 6. So here's 6, so I'll put a dot there as well. But the function near 2 should be pretty much 3. So if here's 3, then I'm expecting the function to look kind of like that. And then I think almost anything I do will be fine. They say just to draw one. There are many correct answers. Yeah, there are going to be just like an infinite number of correct answers. So any function which does kind of anything at all, here we go. Undefined at 0. The limit as x approaches 0 is 4. F of 2 is 6. But the limit as x approaches 2 of f is 3. This was actually quite easy. Okay, 33 I think is quite hard, but we did a problem almost exactly like this, and I think more than anything else, these kinds of problems are what get you to really understand the epsilon delta definition of a limit, which is arguably, important. Okay, let's go. First they give you a function, f of x equals 2 minus 1 over x, and textbooks are trying to save space and stuff, so instead of giving you a gigantic picture, they give you a little tiny picture, and then they zoom in on it or something. Alright, but we're not constrained by that. So here are the actual directions. The directions are, they come in verbal form. It says find delta such that, I'm writing this almost exactly, if, they say, the distance between x and 1 is between 0 and delta, then the distance between f of x and 1 is less than 0.1. Okay, so this is the other way of phrasing the epsilon delta definition of a limit, as I sort of warned you about or something, with absolute values. So I find it maybe a little bit harder to understand, but not too hard. So okay, let's try to understand it. What ultimately does this mean? Sort of think about this or look at this for a minute, and here's what this basically says. Find a delta such that if you are within 1 of delta, then the gap between your function and 1 is less than 0.1. So what's really going on here? What's really going on here is an epsilon challenge has been issued, and the epsilon challenge that has been issued is for epsilon equal to 1/10. And what we must now do is find our delta response. In other words, this is exactly like that 20-minute video that I posted last week called something like a more difficult example, in which you are given a non-linear function and asked for a particular epsilon challenge to find the delta response. It's almost the exact same problem. Now you just have to do it yourself to see if you could get it. And okay, let's go. So now I shall make a sort of very large picture of this function. 2 minus 1 over x. What's it going to look like? Well, I think we know, right? All the action appears to be happening at 1, 1. So that's nice, or maybe confusing, I don't know. So there's 1, 1. And what is this function like? Well, it's a negative 1 over x function, so it's going to look, no, it's going to look like this. And in fact, sorry, what am I doing? Yeah, it's going to be 2 minus 1 over x. So, right, so there's kind of a horizontal asymptote at y equals 2, but when you plug in 1, certainly you get back 1. There will also be a vertical asymptote at x equals 0. So I think I got this under control. If you plug in, well, I guess if you plug in 1/2, you get 0. So maybe that's worth it to put a dot there. And by the time I get out to 2, I'm going to be at 3/2. So alright, this is just me trying to make my graph accurate. So we got something that looks like this. Okay, great. And pictorially what's going on is that, like I said, we received an epsilon challenge. What is that epsilon challenge? It's to get within 1/10 of 1. So let's do it. Picture not totally to scale, but not so bad either, because I made my picture kind of so big. What is this? This is 1 minus a tenth, 1 minus a tenth, and this is 1 plus a tenth. And so what's really going on here is we are taking the limit as x approaches 1 of this function 2 minus 1 over x. And of course the answer is 1, we would like to say, but to back up this assertion, we will accept any epsilon challenge and we'll find a delta response. But for this particular problem, we're just finding a response for the particular epsilon challenge of 1/10. Okay, so how should I respond? And the whole question is over as soon as you can answer how close to x equals 1 must I get in order to guarantee that my answers are within 1/10 of 1. And just like in the video, let's ignore the sort of silly but technically correct answer of just saying delta equals 1 over a million. That will work, right? It is true that within 1/1,000,000th of 1, the outputs will be within 1/10 of y equals 1. But that's kind of like a not intellectual or interesting way of interpreting the problem. So for problems like this, and I will be more explicit when I ask you to do problems like this, I will ask for the largest possible delta which works. So in other words, how close? What is the symmetric interval around 1 in which I can guarantee that this is true? Okay, let's do it. Well, ultimately, I just need to solve a little inequality by working backwards, right? So I say, okay, under what conditions is my function between 1 minus a tenth and 1 plus a tenth? Okay, what is my function? It's 2 minus 1 over x. Alright, so that's like 9/10, and this is 2 minus 1 over x, and this is 11/10. Okay, so we continue by just solving this inequality. So subtract 2 from all three sides of this inequality. That gives me something. Let's see, if I subtract 20/10 here, I guess I get negative 11/10. And here, if I did that right, I suppose I did. Sure. Yeah. And here, if I subtract 20/10, I get negative 9/10. Alright, so this is enough algebra that I sort of can really do it in my head. Maybe not, maybe so. Now what? Well, let's just continue the algebra. I can multiply through by a negative, which flips all the signs. So then I get 11/10 is less than 1, no, is greater than 1 over x, which is greater than 9/10. And now I have an inequality which says that 1 over x is between 9/10 and 11/10, so it's certainly positive. Therefore, all three sides of this are positive, and the fastest way to deal with this situation is just to perform reciprocation. If everything's positive, then when you reciprocate both sides of an inequality, you flip the sign, and so what we get is 10/11 is less than x, which is less than 10/9. Okay. And so I sort of got the answer to my question. My question is, for all x values between 10/11 and 10/9, we're good. And it might be worth it to sort of think about, like, well, what is 10/11? That's just 1/11 less than 1. So maybe we even want to write this as 1 minus 1/11th. And what is 10/9? Well, that's 1/9 more than 1. And so we have the following situation. The situation is that on the left-hand side of 1, let me now erase this, problem's basically over, but we still need to kind of talk it out. On the left side of 1, it seems that I can go back an 11th. So what is this point? This is 10/11, a little bit less than 1. And what that means, if you add it to the picture, is that this point here must be the point 10/11, comma, well, that's 9/10. 9/10. And you can even just double check that by plugging 10/11 in here, right? 2 minus 1 over 10/11 is like 2 minus 11/10, which is 9/10. Okay, great. And so this this distance here, I'll maybe do it in red now. This distance is 1/11. Chop. And yet on the other side, I shouldn't expect it to be symmetric because this is not a line. It's a non-linear curve. On the right-hand side, I can go all the way out to 10/9. And all right, if I'm trying to do this to scale, then it's not really clear that this is bigger, but of course this is a little bit bigger, right? 10/9. And that means that I have this point up here, going really slowly, so everyone will get it. This point up here is going to be 10/9, comma, well, then I'm going to get 11/10. And you could even plug in 11/10, and you see that 1 over that is 10/11, 2 minus, plug in 10/9, I mean, and 1 over 10/9 is 9/10, 2 minus 9/10 is 11/10. So you could even have skipped all of the inequality stuff over there and simply drawn a really good picture and set this function equal to 11/10 and 9/10 and solved for these x values and just added it to the picture. That would have been another way to do the problem. I'm kind of doing both of those things. So what does that mean? That means that on the right-hand side of 1, I can go as far out as 1/9. And so the full answer to this problem in a kind of casual, informal way is that if I want to meet this epsilon challenge, I can drift left by 1/11 and I can drift right by 1/9. And so you might think that that's like kind of the answer or something like that. Or as some people say when we do this live in class, you know, there are 2 deltas. Okay, but there are not 2 deltas because built into the definition of the epsilon delta definition of a limit is that there be a single delta. So you need to kind of respond with a single number, and that number tells you how far you're allowed to go from 1 in a symmetric way. And so the answer now, I hope everyone realizes, is just, I think, common sense that if I'm allowed to go left 1/11 and I'm allowed to go right 1/9, then we need to choose the smaller of those 2 numbers, and we need to be conservative and just answer 1/11. What is 1/11? 1/11 describes is the correct answer to how far out I can drift from 1 on both sides and still land between the parallel lines. Okay, so this answer I'm going to give here, instead of 10/11, this is going to be like 12/11. And it certainly is true that if I stay between 10/11 and 12/11, that all of those values, when plugged into the function, will land between the parallel lines. And therefore, the answer to this problem is set delta to be 1/11. That's really all you actually had to do. Good. You did not have to do the proof that this actually works, which I did in the video from last week, so I won't redo that here. Okay, good. That was section 2.2. Let me pause the video and come back for the other problems. Okay, we're back. Section 2.2 was kind of the theoretical approach to like what is a limit, including the epsilon delta definition. So there were lots of kind of just
draw a picture type problems or look at a graph and do it. Section 3.3 is called something like evaluating limits analytically, which means that we are now going to use kind of algebraic techniques to decide what the value of limits are. And this is arguably, the more important skill. So let's go. These were all kind of like very easy, so let's just sort of do them really fast. I'm skipping all of these because they were all just like continuous functions where you just plug in the number. So these four are slightly interesting. Let's do them now. What is the limit as x approaches 0 of root x plus 5 minus root 5 over x? Alright, well, the first thing you should think to do is just plug in 0 for x. Well, if you just do that, what happens? Well, you get root 5 minus root 5 over 0. So you have a kind of a 0 over 0 situation. And so this happens so many times, this 0 over 0 situation. And I think we made a big deal on the second day of this class that that you don't know. When you have a 0 over 0 situation, you don't know the answers. So what must we do? We must go back to work and try something more careful to figure this out. In other words, algebra. And here, I think in a previous video, I made a kind of a plea that the only way we're going to make progress here is to kind of unlock what's going on inside the square root, and so we have to multiply by the conjugate. So this is a sort of an algebraic trick. I don't like to think of it as a trick. It does feel a bit like a trick, though, if I'm being totally honest. It's a trick that if you think about it and talk about it, which I did in that other video, you can sort of see why you kind of must do this, actually. But all right, once you've seen it before, now we can just do it. Why does multiplying by the conjugate magically solve everything? Well, it just does. Watch and see. Here we now have the limit as x approaches 0 of, well, that numerator is now a difference of squares. That's the whole point of multiplying by the conjugate. And so we get up top x plus 5, but then just minus 5. Maybe I don't even want to, so I'll just go with x because that's what it is, x plus 5 minus 5. And on the bottom, I have x times, don't bother distributing it, because the very next thing that's about to happen is that we cancel the x's. And now we have a limit which is no longer indeterminate. It's the limit as x approaches 0 of 1 over root x plus 5 plus root 5. Yeah. And what is that? Well, when I plug in 0, now I get 1 plus root 5 plus root 5. So that's 1 over 2 root 5. And personally, we're big kids now in calculus and stuff, so I don't think we need to waste time in our lives, rationalizing. That's kind of like for little kids. So I'm done. I'm just going to leave it like that. Okay, more. 57, what now? Similar kind of problem if I just naively try to plug in 4. Then I get root 9, which is 3 minus 3, so that's pretty much 0. And the denominator is pretty much 0 also. So we are once again in a 0 over 0 situation, which does not mean that it's 0 over 0. 0 over 0 situation is just a way of saying the numerator goes to 0 and the denominator also goes to 0. What's the answer? I don't know. We got to find out. And the way to find out is, again, to do some algebraic simplification. And once again, the way to do this is by multiplying by the conjugate. So I will multiply the top and bottom by x plus 5 plus 3 and root x plus 5 plus 3. That's going to unlock the information up there. And all right, what do I get now? Well, up top, I get, so this becomes the limit as x approaches 4 of, in the numerator this becomes x plus 5 minus 9 over, and now on the bottom it really does make sense to just like not simplify, just leave it as x minus 4 times root x plus 5 plus 3. Because what do you get up top? Well, you get x minus 4. And so it cancels, kind of skipping one step here because it makes this less cramped. Then this just becomes 1 over root x plus 5 plus 3. And so what did I do? I canceled the x plus 4 on the top and the bottom, so it really does seem like magic, this multiplying by the conjugate thing, because now I have a limit which is not indeterminate, and if I just plug in 4, I get root 9, which is 3, so that's 1 over 3 plus 3, so this just is 1/6. Cha, cha, cha. Okay, good. More. What now? Well, 59 says, that's just not in love with my spacing here, but it's kind of okay, I guess. So 59 says, do this limit. Well, once again, if I try to casually plug in 0, I get 1/3 minus 1/3 on the top, and 0 on the bottom. So this is yet again a 0 over 0 situation, and so I have to do something. What can I do? Answer, do some algebra. And in this case, the algebra that I should do, I think, is just simplify this complex fraction. So get a common denominator up top. This is what I'm going to do. Multiply by 3 plus x over 3 plus x, and here multiply by 3 over 3, and just get a common denominator. So what do we end up with? It's the limit as x goes to 0 of 3 minus, being careful now when I distribute the negative, that's minus 3 minus x all over 3 plus x. But then all of that is all over x. So note my use of sort of like the large bar here to indicate that it's like this. Okay, well, now doing some more fraction simplification, what does that mean? It means I have negative x up top, and on the bottom I have 3x, x plus 3. Hopefully you can follow all this. This is just kind of basic algebra, rational function manipulation. Well, now the x's cancel, and I am left with something which is not indeterminate. It's just negative 1 over 3 x plus 3, and now when you plug in 0, you get negative 1 over 3 times 3, and so the answer is negative 1/9. So that was pretty straightforward. And 61 is actually a very easy problem, but I think something that I've noted in the past that students got confused, because it is kind of confusing, which is that your book wants you to get used to this delta x thing as being like its own special symbol. So don't decompose it in any kind of way or anything like that, or overthink it. It's just like a variable, totally distinct from x. In other words, if you don't like this, you might very well just substitute in some other variable. The limit as h goes to 0, say, of 2x plus h minus 2x over h. And this is precisely the same thing. I've just replaced every delta x with an h. So this, to me, actually is more clear. If I was going to write this textbook, I would just never do this, but our book is going to do it, so maybe we should just all kind of get used to it. So that's kind of all that means. All right, having rewritten the problem this way, hopefully everyone agrees it's easy. If you try to plug in 0 for h, then once again it's a 0 over 0 situation. How can we deal with that? Well, here it's even easier than before. There's no algebra even to do. Just kind of distribute, and you get 2x plus 2h, well, minus 2x all over h. And so actually this just becomes the limit as h goes to 0 of 2h over h. And so this is just 2. And that's really all there is to say about this problem. Okay, good. That was the problems that I thought were worth doing from this, worth going over from this homework assignment. We're going to hand this in today. Goodbye. Nice short video.